What if the internet wasn't really built on code, but on chaos? Today, we're going to dive into the secret math that keeps our digital world from grinding to a halt in one massive global traffic jam.
Oh man, we've all been there, right? You're in the middle of a super important video call, and then, boom, frozen screen, that face. It's got to be one of the most annoying, universal glitches of modern life.
But here's the thing. That freeze, it isn't just some random glitch. Nope, it's actually a tiny symptom of a huge problem we call digital chaos. And this is happening all the time, on a scale that is, well, it's literally almost impossible to wrap your head around.
So think of it this way. The internet is basically one giant chaotic superhighway. You've got billions of data packets, little bits of your video call, your emails, even this content right here. They're all zipping around at the speed of light, and every single one is screaming, "Get me there now." So the big question is, how on earth do we keep this whole thing from turning into the world's biggest traffic jam?
Well, it turns out the answer isn't as simple as just adding more fiber optic cables or building faster computers. The real secret? It's math. A really powerful mathematical toolkit that was designed for one specific purpose: to find order in all that randomness, to tame the chaos of the internet. Okay, so the official name for this toolkit is Stochastic Performance Analysis. I know, it sounds super complicated, but the core idea is actually pretty straightforward. It's all about using math to predict how these incredibly complex systems are going to behave. Everything from one single server to, the entire internet.
And here's the key. That big word, stochastic, it just means random. That's it. So this whole field is about applying the science of probability to networks. It lets engineers get ahead of the game. Instead of just reacting to problems after they happen, they can actually predict them and build systems that are designed from the ground up to handle the totally unpredictable nature of internet traffic.
So if we open up this toolkit, we find three main tools inside. You've got your basic probability theory, of course. Then you have something called stochastic processes, which is all about modeling random stuff over time. And finally, my personal favorite, this really cool concept called queuing theory, which is literally the science of waiting in lines. We're really going to focus in on those last two.
All right, let's grab that first tool, stochastic processes. Think about it. How in the world do you create a model for something that is by its very nature unpredictable? Like, how do you predict when the very next data packet is going to show up at a server?
Well, that's exactly what these processes are for. They're these incredible mathematical models that don't try to predict one single definite future. That's impossible. Instead, they map out all the possible futures and tell us how likely each one is. It's the language we invented to describe and really understand randomness itself.
And what's cool is that this math gives us different ways to model different kinds of randomness. Take the Poisson process you see on the left. It's perfect for modeling things that happen in sudden, separate bursts, like data packets hitting a router. It's all jumpy and discrete. Then you have something like Brownian motion on the right, which is totally different. It describes a slow, continuous, wandering kind of change, kind of like the drift of a stock price. See? They're both tools for understanding chaos, but they capture completely different flavors of it.
Now, within all these models, there's one absolute superstar, the Markov process. And its genius is just how simple it is. It works on one key assumption. The future only depends on what's happening right now, not on anything that happened in the past to get here. This memoryless quality, as they call it, makes it a shockingly powerful and efficient tool for modeling all kinds of things, from network traffic to even weather patterns.
Okay, so we've got a way to model all this random data showing up. But what happens when a whole bunch of it shows up at the exact same time? That brings us to the next amazing tool in our kit, the science of waiting in lines. Seriously, it's the math of queues. And it doesn't matter if you're talking about people lining up at the grocery store or a flood of data packets hitting a server, the basic problem is exactly the same. You have things arriving, you have a period of waiting, and then you have a service. Queuing theory is what gives us the mathematical tools to break down and, optimize this whole process.
So, the anatomy of a digital queue is pretty simple when you break it down. First, a request arrives. That's you clicking a link. Then it hops into the queue, basically waiting its turn. And finally, the server gets to it and processes the request. Every single thing you do online goes through millions, maybe billions of these tiny invisible waiting lines.
But that brings up a really important question. This isn't just about making things go fast. It's also about making them fair, right? How do you stop one person's massive 4K movie download from totally hogging the line and blocking everyone else's tiny email? How do you design a system that's fair for billions of data packets all competing for the same resources?
Well, the answer is pretty subtle, and it's pure math. It all comes down to this. Predictability is the core of what we perceive as fairness. I mean, think about it. A system feels fair if everyone has to wait roughly the same amount of time. And that's why engineers obsess over something called the variance of the waiting time. If you have low variance, things are predictable and feel fair. But if you have high variance, it's total chaos. It feels unfair, even if the average wait time is technically the same.
All right, so let's recap. We've got these incredible tools. We have stochastic processes to get a handle on randomness, and we have queuing theory to manage all the digital lines. So now, let's see what happens when we actually put them to work.
By using all this math, engineers don't have to just guess anymore. They can develop what the source material calls near-optimal control heuristics. And yeah, that's a super fancy phrase for a simple idea. They can create smart, simple rules of thumb that help guide the network to behave in a nearly perfect way, even when conditions are totally chaotic.
And you better believe the applications are everywhere. This is the math that helps manage servers so they don't get bogged down when they're busy. It's used to create the policies that prevent those digital traffic jams from ever even starting. It even lets us create really good guesstimates for systems that are just way too complex to solve perfectly. And at the end of the day, it all adds up to a faster, more stable, and, yes, a fairer internet for all of us.
So let's bring this all the way back around to where we started. The next time you're streaming a movie or you're on a video call and everything is just perfectly smooth, crystal clear, no buffering, no weird glitches, none of those frustrating freezes.
Just take a second and remember that this seamless experience is not an accident. It's the result of decades of absolutely brilliant mathematical work. It's this whole hidden world of probability and queues, silently, constantly taming the digital chaos behind the scenes.
You know, our entire digital world is fundamentally built on this mathematics. But as we keep connecting billions and billions more devices, as the network gets infinitely more complex, you kind of have to wonder, right? What happens when the chaos finally starts to outgrow our tools? What happens then?